Hello, I'm excited to present Image to Sphere, Learning Equivariant Features for Efficient Pose Prediction. My name is David Cleve from Northeastern University. This is joint work with Andre Biza, Robert Platt, and Robin Walters. Pose prediction is a challenging problem with applications in fields such as robotics and artificial reality. In the context of this work, pose prediction aims to predict the 3D rotation of an object from a single RGB image, where the rotation is relative to some canonical orientation defined in advance. Standard regression methods struggle in the open world setting where a single true rotation may not exist. Many common household objects like bottles, boxes, and mugs have rotation symmetries or exhibit pose ambiguity from certain viewpoints. In other cases, the image may not convey all necessary information to determine the pose. Rather than regress to a single point estimate, it would be useful to explicitly model a distribution over correct rotations. Unfortunately, it is difficult to learn distributions over SO3. Bingham and Fisher distributions are simple to parameterize but lack expressivity. Extending to multimodal versions introduces training stability and is not always clear how many modes to include. For example, consider the range of object symmetries even within the class of tables shown on the right. And most importantly, lots of data is needed to fit distributions over a large space like SO3. We aim to address these limitations with image to sphere, a method that learns SO3 equivariant features to efficiently represent distributions of 3D rotations. It captures the underlying SO3 symmetry of the problem and represents complex distributions compactly using the Fourier basis of SO3. Our method achieves state-of-the-art accuracy on the Pascal 3D Plus dataset and produces detailed distributions with fewer examples than competing baselines. Before introducing the method, I will provide necessary background on equivariance and group convolution. An equivariant mapping preserves symmetry. Pose prediction exhibits 3D rotation symmetry. By rotating the object, we also rotate our prediction of its pose. We can construct equivariant neural networks to preserve symmetry by stacking group convolution operations. 2D convolution is a well-known instance of group convolution, where the filter is shifted in the 2D plane. For this work, we're interested in SO3 group convolution, where the filter is defined over the sphere or SO3 and rotated in 3 dimensions. Equivariant networks are useful since they have higher sample efficiency due to the generalization to transformations of the input. Convolution with continuous groups can be efficiently performed in Fourier space using the convolution theorem. To make the computation tractable, the representations are expressed using a truncated Fourier series. On the right, we illustrate the Fourier transform of an S2 signal into spherical harmonics with degrees 0 through 3. In the literature, the benefits of SO3 group convolution have only been explored for 3D input representations such as point clouds or 360 camera images. Our work presents a hybrid equivariant approach that learns a representation in an SO3 transformable space such that equivariant processing can be utilized. First, visual features are extracted using a conventional convolutional network. The image features are projected onto the sphere. Then we perform SO3 group convolutions in the Fourier domain. The output is transformed back to the spatial domain to produce a distribution over SO3. We project learned features from image space to the 2-sphere using an orthographic projection illustrated here. The projection is simple and maintains spatial relationships encoded in the feature map. We will show later that this projection achieves higher performance than alternatives. Once the representation exists on the sphere, we can perform SO3 group convolutions. The representation is stored in the Fourier basis up to degree 6. A nonlinearity is applied in the spatial domain using the inverse Fourier transform. These equivariant layers improve generalization capabilities of the network with minimal compute cost relative to the convolutional encoder. We construct a distribution over SO3 by performing inverse Fourier transform onto a uniformly spaced grid over SO3. Such a grid can be produced at different resolutions using the heel-picks method pictured on the right. A softmax is applied across the grid to generate a categorical distribution. The model is trained end-to-end to minimize the negative log likelihood of rotation labels. Interestingly, the model can be trained using a sparse grid but still make accurate predictions over a denser grid at inference time. We evaluate the accuracy of our method on the challenging Pascal 3D Plus dataset, which contains real images shown on the right. Since object symmetries were broken during the manual annotation process, we see that regression methods can be competitive to distributional learning methods. We find that our method, image to sphere, outperforms the baselines with a median rotation error of 9.8. We attribute image to sphere's performance to the improved generalization capabilities of the SO3 equivariant layers. When we examine the output of image to sphere on Pascal 3D Plus, we see that it naturally models uncertainty. For instance, in the top left, a bimodal distribution is predicted since the model cannot perfectly determine whether the bus is facing towards or away from the camera. Being able to model uncertainty in this way could be beneficial in fields like robotics to make policies more robust or stable. The distributions are visualized here using the approach from Murphy et al., where three Euler angles are plotted as latitude, longitude, and color respectively. The ground truth rotation is shown as a ring. We further evaluate the distributions produced by image to sphere with the SimSol dataset, which includes synthetic renderings of objects that have pose ambiguity due to symmetry or self-occlusion. The dataset provides the full set of valid rotations associated with each image, so we can quantitatively evaluate the accuracy of the learned distributions using average log likelihood. Here we show the distributions produced by image to sphere. In the top left, it is accurately modeling all 60 symmetries of the icosahedron, and in the middle row, it models objects that are symmetric along one axis, like a cone or cylinder. When restricting the training data to 10K images per object, we find that our method achieves higher average log likelihood than the next best baseline, Murphy et al., which uses an implicit model to parameterize the distribution. This experiment shows that our method is the most sample-efficient and expressive approach to modeling distributions over 3D rotations. The results so far support the benefits of leveraging SO3 equivariant layers, but there is still the question of whether there is a better way to learn SO3 equivariant features from 2D images. In this experiment, we compare against three alternatives. To restate, our approach projects features spatially onto the sphere. We also evaluate the performance when projecting to the spherical harmonics, to the Fourier basis of SO3, and to the largest discrete subgroup of SO3, the icosahedral group. Our proposed approach achieves the lowest rotation error. We hypothesize projecting to the sphere is best since it preserves spatial information that exists in the extracted feature map. To conclude, the success of our method, image to sphere, suggests that SO3 equivariance is beneficial even if the model is not end-to-end equivariant. We find that the Fourier basis of SO3 can efficiently represent complex distributions. We hope that our approach can be adapted to other applications where 3D reasoning from 2D inputs is desired. In future work, we plan to extend the approach to 6D pose estimation using the SE3 group. For the full paper or code implementation, please check out our website. Thank you.